In this video, we're going to look at some details of production functions, and specifically, we're going to focus a lot on looking at isoquant curves and focusing on MRTS, which is the marginal rate of technical substitution. It's very similar to the idea of marginal rate of substitution along an indifference curve in utility theory. We call it marginal rate of technical substitution to reflect the idea that we're talking about a production function. And we'll also highlight this idea of elasticity of substitution. But first, let's just look at a production function. Now, this is one that is a little bit not typical. It's an atypical kind of production function. Don't worry about, this functional form. This is kind of wacky, but the reason is, just to start, I wanted to look at a production function that, or a production hill, as we call it in 3 dimensions here, where if we think about labor increasing along this axis and capital getting bigger along this axis, and the amount that we produce, Q, increasing as we get higher up the hill, this one's an interesting one to think about to start because it actually has a maximum. A lot of times, or probably most production functions that we will be looking at, do not have a maximum point and then start going back down. This implies that at some point you can increase your capital and labor up to a point that maybe there's a third input, factory space that you're thinking about, floor space. And you can get so crowded that perhaps after you reach this maximum point that looks to be around 190 units of output, that might be somewhere around 25 units of labor and 25 units of capital. We'll look at this more specifically down below here. That beyond that point, your production actually starts to drop as you add more labor or drop as you add more capital. You're just getting too crowded, perhaps. Now again, usually we assume that more inputs will result in more output, but that doesn't always have to be the case. So we'll start here and look at some of the interesting features that are going on here. Now, just like when we're talking about looking at utility theory, where there's more good X and more good Y that cause utility to increase, usually what we do is we turn this shape and we look at it from the top down, and we look at these level curves. In other words, this brown level curve right here is the same as this brown line that runs, I'm just underlining the brown line that goes around toward the bottom here, right? So that green line is below the brown line. That brown line tells us all of the combinations of labor and capital that could produce 10 units of output. And when we turn it up to where we have an overhead view, it's a little easier to pick out exactly what all those X and Y points are. So I'll just kind of draw a line on top of that brown one to highlight it there. And so we get to see a lot of different combinations. For example, approximately 10, and we're going to be putting labor on the x-axis and capital on the y-axis. 10 labor and 5 capital will give you 10 units of output. Similarly here, let's see, maybe 20 capital and, I don't know, 3.5 or so on the labor axis would be able to give you 10 units of output. And similarly, as you go up here, you're getting higher and higher levels of output. Now, what are some things we should be thinking about in addition to the obvious? Well, one thing that's very similar, as I mentioned before, to utility theory, and I mention this because in most micro classes, you look at utility theory first and then production theory later. We have the marginal rate of technical substitution, which is the marginal product of labor divided by the marginal product of capital, and it tells us the slope of one of these isoquant curves. And if you haven't heard that term isoquant before, isoquant is just the prefix iso, which means same, and then quant for quantity, isoquant. And each of these lines tell us the combinations of inputs that give us the same quantity. So 10 for this one, and then we can look at the little key up here, 20, 30. So these go by tens on both figures. So this one would tell us all the combinations for 20 output and 30, etc. Now, interestingly, as we saw on this hill, there is this maximum, this little blue ring, that's the maximum output we can get, is 190. We might be able to get a tiny bit more if we were exactly in the center there, maybe 191 or so. And we see that same blue circle right here. So all of these combinations give us 190 units of output. Hypothetically, there's some higher level that might be exactly in the center there. But with this kind of production function where you can have too much of an output, or sorry, input, not output, but too much of an input, and sometimes increasing an input can actually decrease your output, we get to see this kind of interesting trend. Let me switch to the color yellow for my ink here. And I just want you to think about a couple of points here and what's implied. Here we're producing, I think, 180, anywhere on this pink line, 180 units of output. And right here we're doing it with approximately 23 labor and maybe 21 capital, just to guess a number there. Compare that point to this orange point over here, where we're producing the same amount because we're on the same ISO quant, but here we're doing it using 27 workers and, maybe 23 machines. Think about the orange point compared to the yellow point. The point that I want you to think about these points is that there is absolutely no reason you would ever want to be at the orange point. Why not? Well, because you're getting the same amount of output at the orange and the yellow. But at the yellow, you must be doing it more cheaply because you're using less labor and less capital. What to look for in a diagram like this is anytime you see an upward sloping part of an ISO quant. Now with indifference curves, we actually say that that's illegal. You can't have an upward sloping indifference curve if both the thing on the x and the y-axis are both goods. But here with this particular production function, we see these upward sloping portions, and that tells you that you never ever want to be on that upward sloping portion. Now similarly, there's an upward sloping portion on the top here, and for a similar reason, we never want to be on these upward sloping parts, because what it implies is that if there's an upward sloping part, if you go down a little bit further and you compare this green point to this blue point, just like what we were saying before about the yellow and the orange, this blue point uses more capital and more labor than this green point, and so you would never want to be at this blue point. So you can just kind of cross off any portion of an ISO quant that has an upward sloping part to it. You would call this a non-economic region, is the technical term for it. Non-economic region. And it just means there's a cheaper way to do it, obviously. It's just very, very easy to see that. Now, the second thing I want to talk about is the marginal rate of technical substitution is the slope of the isoquant. And again, the positive here we'd never want to be on. But let's take a minute and interpret what we're looking at here with the marginal rate of technical substitution, just by looking at a couple of points here. So let me erase a couple of, let's erase this green here, and let's look at this pink line, the downward sloping part of the pink line, because that's normally the region that we're going to be interested in. And let's consider 2 points on this pink line. Let's see, here's 1 point, and here is another point. Okay, let's just look at between those 2 points, and let's look at the slope between those 2 points right there. Looks like we're going from maybe 6 to 7. Let's just say that 6 to 7 laborers. And that allows us to, when we go from adding our 6th laborer to our 7th laborer, it allows us to give up how many machines? Well, we can see we're going from 20 to 15 machines. So what's the slope? Well, rise over run here is we're going down 5 and we're going over 1. So rise is -5 going over 1. That slope, which is the same as the marginal rate of technical substitution, is -5. MRTS equals -5. Now generally, even though we know it's negative, we will just talk about marginal rate of technical substitution as being the positive number. And so we'd say the marginal rate of technical substitution is 5. What does that tell us? Well, let me tell you 2 ways to interpret that slope or that number in these sentences right here. You can interpret it either as, and these are basically saying the same thing, it's the rate at which capital can be decreased for each 1 unit increase in labor for the same output. And that's exactly what we were saying here. We're on the pink line, which I think is 10, 20, 30 units of output, and we can get 30 units of output in this region either with 6 workers and 20 machines, or 7 workers and 15 machines. So the rate at which we can exchange workers for machines is 1 worker will replace 5 machines. So we can say here we can decrease 5 capital for each 1 unit increase in labor. Or, going the other way, from 7 back to 6, we can interpret it this way. It's the rate at which capital must be increased, 5, for each 1 unit drop in labor to keep the same output. So that's what the slope of these isoquants is telling us, the marginal rate of substitution, or technical substitution. It's the rate at which you can switch those 2 things. Now, another thing that people talk about a lot when you're talking about production functions is, in a particular kind of production process, is the capital labor ratio. And in my classes, I always spell capital with a K, as I believe you do in German, even though in the United States we use a C, because we always, instead of using C for cost, we use K for capital, even though capital starts with a C in English. So we talk about the capital labor ratio, K over L. It's just the ratio of how many machines are we using to how many workers are we using at a given point. And a way to visualize that capital labor ratio is the slope of a ray from the origin to a point. So let's look at that real quickly. So let's suppose we were at this point, this first blue point. Let me erase some of this here. Okay, so let's suppose we were at this blue point where we're using 20 machines and 6 workers. Are we in a very heavily mechanized industry, or are we in a labor-intensive industry? Well, you can tell here that if we're using a lot more machines than people, we must be in a heavy machinery-oriented industry instead of a heavy labor-oriented industry. And a way to visualize K over L, which is just going to be 20 over 6, which is going to be approximately 18.33, right? We'd say that's the capital to labor ratio. 18 machines per worker. Oh, I'm sorry, that's not 18. That should be 8. Sorry, 8 machines per worker. 8.33. You can visualize how capital intensive an industry is just by drawing a line from that point to the origin, right down there. So that's a ray. And as that ray gets steeper, you're using a higher ratio of machines to people. As it gets flatter, you're using a lower capital to labor ratio. So for example, if we went right over here to this point, the slope of this ray is very flat, and the capital labor ratio is 5 over 10, or 1/2 of a machine per worker, right? And so the flatter the ray, the lower the capital labor ratio. It's just a way to picture that very quickly. And that's going to be useful in just a second because we're going to talk about a kind of complicated idea. It's going to take you a few minutes in thinking about this to digest this idea. So now that we know what the marginal rate of technical substitution is, it's the slope of an isoquant. And we know the capital labor ratio can be pictured as the slope of a ray from the origin to a point. Now, here comes an idea that is called the elasticity of substitution. The elasticity of substitution is asking the question, how easy, let's start with the interpretation, can we easily substitute between capital and labor or not? Are we in an industry where we could easily say, oh, a machine broke down, just get one more person or a couple more guys? Or a couple of people don't show up for work, you can easily replace them with a machine. So are you in an industry that's easy to substitute between labor and capital or not easy to substitute between labor and capital? Before we talk about measuring this, let me just draw you a couple of pictures and think about the difference here. So let me give you two kind of extreme cases here. Let's look at a production function that involves perfect substitutes. Perfect substitutes. This means that it's easy, very easy to substitute between capital and labor. For example, the most simple case you could think of is suppose we had two kind of workers, people who are very fast and strong and people who are very slow and weak. Okay? So we can call those high quality workers over here and low quality workers over here. These two kinds of workers might be perfect substitutes, whereby if you have one high quality, strong, fast worker, you can always substitute them with two slower, weaker workers. And you can always substitute at this rate of one high skilled or fast worker to two slow workers. And another, so this would be an isoquant, would be a straight line. Or we could have, if we had two high skilled workers, we could produce the same amount as if we had four low skilled workers, or one high and two low. That would be a higher isoquant there. And you get the picture. So if we had four high skilled workers, we could replace them with 8 low skilled workers, or 3 high and 2 low, or 2 high and 4 low, or any linear straight combination in between. I'm trying to draw a straight line there, even though it doesn't quite look like it. So in a production process with perfect substitutes, this elasticity of substitution number is going to be very high because it means you're very flexible. You don't care if you have machines or people, or you don't care if you have high or low skilled workers. As long as you have the right total, you're fine. It's very easy to switch between these. So if the low skilled workers are hard to get or too expensive, you can go with all high skilled workers very easily. The opposite case of perfect substitutes is a production process where you might need perfect complements. Perfect complements. So there's a lot of similarity in the thinking here between consumption and production. So let's think about perfect complements. These kind of production functions, instead of calling them perfect complements, which you can, that's fine, perfect complements, I'll abbreviate that. Sometimes people call these kind of production functions Leontief, L-E-O-N-T-I-E-F, production functions. I'll just abbreviate that PF. A Leontief production function is named after an economist named Vasily Leontief, and it involves perfect complements. For example, you might have a production process where for every, let's go back to capital and labor, that for every machine you have, you must have 4 workers, right? And perfect complements would imply that they have to be in exactly that proportion. You can't produce any more if another guy shows up. You're on the same isoquant. You might have 5 workers. Well, let me move that over there a little bit. So, okay. So, whoop, L, I'll label it over there. If you had 5 workers in one machine, you get the same output as if you had 4 workers in one machine. Because we're thinking about a type of machine here where you need exactly 4 workers and the 5th person has nothing to do. And if you get a 6th worker, 7th worker, and you only have one machine, you can't get any more output. So the isoquant is going to be flat. Now, if you had, similarly, 2 machines and 4 workers, you'd get exactly the same amount of output also. You're not going to get any more output until you get to the ratio of 2 to 8. That would be a different isoquant with a higher level of production, and it would be another L shape like this. More workers are not going to do you any good without more machines, and more machines do you no good without more workers. You get this perfect complement where the inputs have to be used in fixed proportions. Now, what's the point of all that? Let's get back to elasticity of substitution. With perfect substitutes, it's very easy to substitute between the 2 inputs because your isoquants are a straight line. Here, it's not so easy. In fact, it's impossible to substitute. There's absolutely no substitution here between inputs because you can't say, for example here, you had 2 machines and 8 workers. Suppose one of your machines breaks. Well, that drops you back down here. And you say, well, one of our machines broke. How about we just get some more workers? And you get more workers and more workers and more workers, and you can never make up for that lost machine. That's what, this difficulty of substitution we're talking about is all about. So the lesson here is the more your indifference curves look like L's, the harder it is to substitute between inputs. The more they are kind of straight lines, the easier it is to substitute. So in the real world, you're probably not going to be in one of these 2 very extreme cases. You're probably going to be looking at something like, here's capital and here's labor, and maybe you have something, here's an indifference curve. Well, this indifference curve in this region is almost a perfect straight line, so that means that it's very easy to substitute between the 2 because it's almost a straight line. Now, on the other hand, if you were looking at an indifference curve that looks more like this, well, that looks much more like an L. And so that's going to be in a situation where it's much more difficult to substitute between the inputs. It's more like one of these Leontief production functions. Now, this elasticity of substitution measure that we usually call sigma, it's the same symbol we use for a standard deviation, sigma, for elasticity of substitution, I'll just abbreviate that EOS, measures along different indifference curves for different functions at different points how close you are. Let me just clean this up a little bit. Are you more like an L, or are you more like a straight line with your indifference curves? And this elasticity of substitution measure, let me just write the formula here because this is probably too small. Well, let me just zoom in here for you. So the elasticity of substitution kind of answers the question to bring this home and be a little more specific. As we use more labor, which changes faster? Our capital to labor ratio or the marginal rate of technical substitution? It's asking the question, which is changing faster? And if the capital to labor ratio is changing faster, that implies that our elasticity of substitution is elastic, and that means we can easily substitute between capital and labor. And the formula we use for this, and I'm going to keep going here for another minute to try to show how this is intuitive. I know it's bringing so many ideas together, it's hard, that we take by what percent at each point, by what percent is your capital to labor ratio changing compared to, a ratio, compared to by what percent is your marginal rate of technical substitution changing. So we're just asking how fast is capital to labor ratio changing compared to how fast our marginal rate of technical substitution is changing. Let's look at these two extreme cases here to see what this means. And so let me erase some of these lines just to make it a little bit easier. All right, let me just draw that one line there. So the elasticity of substitution, let's just write that formula here again, is the percent change in the capital to labor ratio divided by the percent change in the marginal rate of technical substitution. So suppose we were moving along this isoquant from here that way. Let's look at what we're talking about in the numerator. The numerator, the capital to labor ratio, let me put a little green star there, and here's, remember the capital labor ratio is looking at the slope of a ray from the origin. So as we move along this direction, look how fast the slope of that ray is changing. Well, it's changing at kind of a moderate rate. As we move down, it's going to get flatter and flatter and flatter. But let's look at the bottom here, the marginal rate of technical substitution. The marginal rate of technical substitution is just the slope of this line, but that's not what goes in the bottom. It's how fast is the slope of that line changing. Well, that's a straight line. The slope is not changing at all. And so if you have a perfect substitutes kind of situation here, on the top, you're going to have a moderate-sized number, right, divided by, well, if it's a perfect straight line, then the marginal rate of technical substitution is changing by 0%, right? And so when you take a medium-sized number and you divide it by a tiny number that's approaching 0, this elasticity of substitution is going to approach infinity. It's going to approach infinity, meaning that the higher number this is, the more you're getting to a situation like perfect substitutes. Okay? Now let's look at this Leontief kind of production function down here. And the same thing, we're looking at the elasticity of substitution is that percent change in the capital to labor ratio divided by the percent change in the marginal rate of technical substitution. So here, instead of looking at a perfect L, let's look at one that's mostly like an L. Okay, so let me redraw this, where this isn't perfectly straight up and down, but it's almost perfectly straight up and down, and then it quickly goes to being almost perfectly flat, but not quite perfectly flat. So let's look at this case right here. And say we're moving from, well, let's go a little bit more toward the middle, where we're looking at that L-shaped kind of bend there. So here we're looking at the capital labor ratio, the slope of that one compared to the slope of that one. How fast is that changing? Well, kind of, not too fast. I mean, that's pretty flat, and that's also pretty flat. So on the top, our capital to labor ratio will be kind of a low-ish number, not too huge. Again, we could call it kind of a medium-sized, or let's just call it kind of a low number on top there. But then look at the marginal rate of technical substitution. How fast is that changing? Well, what we're looking at here is how fast is the slope of the isoquant changing. Here it's very steep. Here it's a little less steep. Here it's a little flatter. Here it's very flat. Between those 2 points, our marginal rate of technical substitution has gone from something very high to something very low. So what we're going to have here is a very large percentage change in the marginal rate of technical substitution. And so what we're talking about here is a number that is close to 0, or very, very small, right? It doesn't have to be 0, but it could be very small. And that very small number is a way to measure the fact that it's very hard to substitute between labor and capital with this kind of Leontief or a similar L-shaped kind of production function. And I know that's a lot to digest, but hopefully that will introduce you to the idea of different shapes of these different production functions, what they could happen, and this idea of the elasticity of substitution here. So just one last time, the higher the elasticity of substitution, the easier it is to substitute between capital and labor. The lower it is, the harder it is. This is Berkey Academy signing off. If you have any questions, please leave them in the comment or question section below, and I'll try to get back to you. Good luck with your studies.